So talk will be some about what we do at NASA with our machines. I mean, they're what they're used for, what the intent is, some of our issues around Infiniband. So Pleades is the system we'll be talking about today. Supports all the major missions in NASA. It's a general purpose resource. If you've got a large project at Ames or within NASA, the whole agency, you'll probably end up on this machine at some point. And in the beginning here, I've got a couple of simulations. And so this is a very large dark matter simulation. It's 50 million light years across, 10 billion particles, generated about 250 terabytes worth of data. And the initial conditions were from WMAP, which is the cosmic microwave background radiation. So you're initializing it using real data, modeling gravity, and then coming up with structures that look very much like what we see when we look up into the sky. And so the importance of these three, I'm going to show three different models that are being used today, is that they're all taking existing data, doing some modeling, and then producing large data sets as a result. So they're driven by real data instead of just simulation. And this process of using existing measured inputs and approximated outputs through simulation is what's driving big data, which our data, when we think about big data, it's that our data sets are getting larger and larger, even more proportionally so than the compute is growing. And a lot of it is that you're increasing the fidelity of the models, but you're also increasing the rate of output, so they're time accurate, trying to get snapshots very close together of how the model is progressing in time. So the next one here is Kepler. So Kepler is looking at a bunch of stars, trying to get transits. So when planets go in front of stars, the stars get dimmer. And if you're looking the wrong way, if the planet's going like this, you won't see it. So it has a cross in front. And so this is a Kepler object of interest. So this is an actual star with a planetary system. And so what Kepler's finding is that there's pretty common to have planets around stars. In fact, probably there's more planets than stars. And a lot of systems have multiples. So this data will be used, to drive future missions. Okay, can we focus on particular planetary systems where we might find an Earth-like planet and be able to image it, or get spectral data coming through it to say there's water in the atmosphere, things like that. But again, this is driven by real data. This is actually an embarrassingly parallel problem. So single-threaded, tens of thousands of processes all associated with stars and catch these transits. This is ECHO, which is a large ocean model. It's an older version of the model. It's a 16th of a degree, and right now we're working on a 48th of a degree version, 100 levels in the ocean. This is there. And so this is, some of this is wind and day-night transitions and flow within the ocean. Very high fidelity global model. And this is actually a big problem on our system right now, and we'll talk a little bit about that. But this, again, is driven by real data. It's satellite data, observational data. The new model is injecting it every 6 hours of model time, trying to model this over some number of years at a 48th of a degree global. So it's a very large, real application, very important for climate and weather. Ocean probably drives most of climate at all of the energy from the sun hits the ocean and is transported to the poles. So that's probably the most important thing to understand about climate. So NASA applications, I mean, they're varied. We run a very wide range of applications on the machines. They go from embarrassingly parallel to compute bound, tightly coupled, data and storage intensive. And really what we're moving towards, again, is towards this more data and more storage intensive. And it's just the way that the models are getting more and more sophisticated about the way they handle data sets. And so our problem is, okay, how do we build systems that can manage all of this data efficiently and move it between all the different heterogeneous elements within the supercomputing environment? Big fast networks are sort of the key enabling technology for that. So 10 years ago, Columbia was really our first InfiniBand-based system. We had multi-rail, SDR InfiniBand, connected up big fat nodes. Sort of an overview of what that was. We had our graphics visualization wall connected through InfiniBand, bridging with Ethernet, and then all the compute elements. And overall, then we moved to Pleades to connect in Pleades and the Hyperwall and all these systems. But this was a very diverse, heterogeneous network, right? So it had InfiniBand, fiber channel, Ethernet, 10 gig Ethernet, all these different networks, a lot of different types of very expensive switching technology, very complicated to maintain, had to have expertise in all of them to sort of operate this. And so architecture target-wise, what do we want? We want all of these compute elements and storage elements and all these different pieces to connect together through some magic high-performance network that's fast and easy to maintain and cheap. And be able to migrate that forward in time. So this is sort of a background of what Pleades is. So Pleades is the underlying network is a hypercube. It's a multi-dimensional hypercube. There's 2 planes, 2 rails. Each bristle on the cube has 9 nodes. And so this is an 11D hypercube, and so Pleades is a partial 11D. It doesn't have quite the number of vertices that an 11D hypercube has, but each of the little red dots is a bristle with 9 nodes on it. And so we've constructed this I/O network that attaches to the hypercube on one of the planes, and this is based on QDR technology. And it was a 3D torus. We came up with some routing algorithms to route between the 2 pieces of the system. And we're currently replacing that. So we're going to migrate off of our I/O fabric, which was a QDR-based torus, to an enhanced hypercube external I/O fabric that's got more 16 switches, and be based on FDR. So just all the speeds and feeds will get faster. And so we're sort of in the process of upgrading that right now. And the Hyperwall as well. So the Hyperwall will be upgraded, still 128 displays, but an FDR-based system. This time it'll be connected on both fabrics, because the visualization piece is, we want to be able to do concurrent real-time visualization. So you're pulling down data sets in real time as they're computed on the supercomputer, potentially saving that off to disk at the same time and visualizing the process in real time while it happens. So Pleades, the initial system, 64 racks, about 393 teraflops in 2008, a DDR-based system. And this is just to give you a feel for how we build systems and build them out and migrate things through time. So it started out 64 racks and then grew to 92, a little bit larger, 112 racks in 2009. That's QDR, so that was a Nehalem-based processor. So we've got heterogeneous system at that point. And added in some more racks. Those are some more Nehalem racks, and then I believe those were actually Westmere's, even though they're the same color. So the system's getting larger and larger over time. Down here at the bottom, that's where we added some GPUs in. So we've got 64 node GPU cluster that's integrated into the system for doing experiments about applications that might be able to use GPUs. And we've since incorporated in 128 node mic system, which is the many integrated core. So just experiments to see, okay, is this a good general purpose resource for scientific use of our applications or not? And we haven't found that they are at this point in time, but they might be, and if they were, then we'd build it out and grow that piece of the system and incorporate it in. The nice thing is once you're plugged into the InfiniBand, you have equivalent access to all the I/O fabric in the system, right? So it's very economical for us to either expand compute or expand into different types of compute and connect it to our all the infrastructure that we have in place. And so this is, we actually deinstalled a bunch of racks in the middle. And so there's cables that go between all these rows. And so this is just a picture of what we had to do to raise the cables, to remove the racks from underneath those cables and install new racks in. Lots of InfiniBand cables. So at this point, when we deinstalled those 64 racks, all the original Pleades system is gone. So it's all been replaced at that point. So talk about Pleades, it seems to be old, but at this point it's all migrated forward. And so we've added file systems and new compute nodes. Majority of the compute portion of the system is based on Ivy Bridge and FDR. And so that process of moving things forward, rolling the system forward, is something that we'll probably continue to do just because of the way that our budgets work and how we get money, how we want to experiment with technology, time our deployment so that we're getting processors or getting network technology at the right time. So now's the time to buy our new file system, right? So we want to sort of decouple that from the compute piece because they probably come from different sources optimally, most cost efficiently. And so again, this is sort of building out, adding in more and more systems. And so today it's 3.5 petaflops, still about 170 racks. So in terms of the network complexity, it's about the same as it was at its peak. They have a little bit more in terms of the number of ports and cables. I think there's about 60 miles of InfiniBand cables here. And so anyway, this is the thing that drives incremental expansion. Spoke to that already, that we really want to time our adoption of different components based on our need, which is budget, requirement from programs, or when technology is available, when's the right time to jump. So the production file system, we have 16 different file systems. So right now our sort of increment for a file system is about 8 petabytes. So the next one we buy will probably be about 8 to 10 petabytes worth of storage. And we can size that based on what's sort of we think the right level of reliability is for the system, what our I/O requirements are, and that'll all plug into our I/O fabric. And then when that system comes in, of course, and as long as we provisioned enough bandwidth from the compute to the storage piece, then we'll be able to, maximize the utilization of what that new technology can bring. We actually use NFS as well, so some applications do better with lots of small I/Os using NFS. We have a little bit over a petabyte file system dedicated to scratch NFS files. It's used for home and system images, and the system overall system size is about 12,000 nodes. So NFS scales to that size without problem. Software environment. Users have many different operating systems that they can choose from. We try to maintain 4 of these, which means we have to patch those. We're probably updating OFED within those operating images. As far as the types of modules that are on the system, we've got 58 different compilers, 26 MPIs, lots of libraries, debuggers, all these different environment elements. And the community on the system is probably about 1,000 users. And so people come and go. It's try to tune it for each of those different communities who have vastly different needs and requirements. So it's really sort of a heterogeneous workload. It's divided up between all these people. So at any point in time, you'd see, between 300 and 500 jobs running on the system, maybe more, maybe less. Some jobs might use up to a quarter or maybe even half, and but the majority of the use is just workloads of codes. And so that's important from a design perspective, because most of what's being done is all interleaved and mismatched together. So you can't really optimize, right? You can't say, okay, well, you fix that. There's too many that's to fix. So it's kind of is what it is. And so what this looks like in the I/O system is basically the I/O's heavily randomized by the time it gets back to the back ends. And so that has some design choices that you make. And the networks also, we can't control flows. Through the application, because the way that you allocate nodes and those sorts of things. But it's highly utilized. So our system is 100% booked all the time. There's a line out the door. And it's in operation 24/7. So that's when we did all of these expansions, bringing in new components or deinstalling, we're doing that live. So we're running work on the system. And that's very important for the OFA to sort of get that concept that in enterprise and in some HPC spaces, we don't take dedicated time on the system. So from a management perspective, for instance, we may have to restart the subnet manager. Well, we don't want every 12,000 nodes, every job to have to come back and access the SA for multicast information, or all the different sorts of things that happen when you hard restart the SM because you had a problem or you needed to change it out. There's a lot of context and things in big systems that are static, and we really want to leverage off of that knowledge and not have to discover everything from ground zero, especially on great big giant systems. It's just not going to work. So anyway, what's a general purpose supercomputer? I think this is HPC cloud. That was on a earlier slide, is that this is HPC cloud. People talk about HPC cloud, but this is really what HPC cloud is today. We'd integrate in virtualization if we could, if it was free, performance-wise, and so we're sort of approaching that, because that has some advantages in terms of how we schedule work, how we could move it around, do maintenance on the system. Is RDMA ready for that? Right, so there's some good progress that's being made in terms of dynamic page registration and dealing with VMs within the context of RDMA. And so it's a technology we'd like to use. It'd be slow for us to integrate it, but we'd take advantage of it if we could. So how does this relate to exascale systems? Well, I think we'll get there to these much larger systems, but we're going to do it incrementally. Probably not going to go buy a giant exascale system like DOE is going to go provision, but we'll be sort of growing what we have cautiously, because the primary focus of our mission is the scientific work that's happening on the machine, and so that's what drives our decision process. And so we have to be a little bit conservative in that regard. That being said, sometimes there's something really important that comes along, and like, you will go do this problem because it's important, and so we have to be ready technology-wise to build a system that's 10 times bigger is sort of what I'd say. Okay, if we were thinking about system is 10 times bigger, what would absolutely break and not function? Because I can't execute on that, right? So we want to be able to say, okay, headquarters says go do this, we can go execute. How would we get that done? And if I can't do that, then we're at a loss, right? So then we haven't done our job properly, really, I think. at that point. So in that context, I mean, so we still have quite a few physical layer issues. I mean, put the cable picture back in here because we do stretch things. I mean, so moving cables around, and sometimes facility people don't understand, fiber cables, and they're moving them around and maybe not being as gentle as they should. But if the system were 10 times bigger, would our physical layer issues really be a showstopper? I think they would, based on the kinds of problems that we have today. And here's a simple example: is so you have a bad cable. Well, there's 4 different places it can be bad, right? At least. So it can be the cable header on one side, or the port on the one side, or it could be on the other side. So which one is it? And so it can take a long time just to diagnose the problem with a single cable. And so let's say I have 100 bad cables, like we do right now, right? Literally have counted them up the other day. I have 100 bad cables. And so really have to come up with a better way to manage physical layer issues that we have in the system. And so diagnostics was sort of, okay, can you even tell me which side of the cable is bad? That would be very helpful. Is it in the cable? Which side is it on? Which port? Light cues, for instance, when an FE comes out, so you have thousands and thousands of cable headers everywhere. It'd be nice if a light flashed and said, this is the one Bob wants you to go change, right? And so there's lights there. And so it's very complicated to map, or just cumbersome to map, GUIDs and port numbers to physical location on the floor, and to get that right every time. And sometimes you make mistakes. It's late. Guys that have been doing this for years go in there and plug a wrong cable, pull a wrong cable, and cause problem. And so just the practical management of it is something that needs work. Human interface issue causes failures, and it can be improved. And so SM support, sort of physical management issues. Jeff Becker has added some things in to subnet management for us to manage cable, so we can down particular cable connections through the subnet manager. So you say, GUID X and port 25, just down that connection, because I'm going to go work on it. So you rescan around it, so when you pull the cable, it's not seen as a trap and a rescan. It's done in a controlled way. And so this reduces packet loss and disruption on the fabric. Subnet management in general doesn't scale. There's a lot of problems in here, and I mean, these are just some of them, and there's been some work in these areas. Scanning the fabric, for instance, just is not going to work at scale. Really need to consider, and I actually have another slide to get ahead of that, but talks some of that scanning the fabric is even problematic. The essay, the way that it's constructed, multicast, restarts. So, like I said, we're in the systems in continuous operation, and so when the system's in continuous operation, you have to have that mindset, no, I can't just shut everything down and go do something. That's never going to happen. If that happens, then it's very disruptive. Packet loss within RC not being reliable. So, I mean, some applications really, really want a reliable mechanism that once they push a packet out, that it gets there and they get a response back and they know that it got there. There's possibility that it doesn't get there, then that can complicate the upper layer a lot. And so Luster does this, MPI does this for efficiency in terms of performance and the amount of code that they're carrying. So if you're going to provide a reliable transfer port, it better be reliable. And it's sort of one of the things that was talked about earlier. Okay, so how do we, and we only want to do this once, that's the other part, right? So we don't want to code the upper layers, we don't want to code the 5 different lower level interfaces. So we're going to develop a new API, we're going to do it once. And if you're going to have a reliable mechanism within that, let's be sure that it tries until somebody above says to stop, not when the layer below says to stop. Just health checking on nodes is incredibly difficult. What nodes are in fact up? I can't tell if I've got a network problem, if the node is up or the network is down or the subnet scanning. Do I have an alternate route? Those sorts of things. And so this is in the bonding area, bonding and performance failure. I want bonding to be performant. I want to get double the bandwidth out of double the channels, and I want it to fail over, and I want that to be transparent. And so this makes just the upper layers a lot easier to deal with. And some of the work that's going on in Linux kernel is really good. Some of these issues may be addressed, but there's still sort of fuzziness up there for application developers. Where do we want to take this? What should we program to? How should we deal with these issues? Is this an administration issue? Is it an application issue? That sort of thing. And here's an example of a problem that we recently found. So this is messages per second for a node based on block size, sort of common block sizes that are transferred. So the fastest was an Ivy bridge running single socket on 10 threads. So not using the other socket at all. And then the next fastest was Westmere, right, in terms of message rate based on block size. So we said, well, hey, what up? Why is this? Turns out there's an issue in the BIOS or some confusion with QPI and sort of Intel thing. They're a little bit quiet about. Hard to get information out, a little confusing. So I think the Narada came out and said there'll be 0.25 microseconds difference to carry this patch. So everybody thought, well, that's a small number. Wouldn't bother with 0.25 microseconds. Well, it turns out it was probably for every cache line or for every something, right? So happened that adds up to be a big number. So when you put this BIOS fix in, then you actually get something out of the second socket. So this is actually what I didn't explain, I guess, was these were the different MPIs, right? So this is Intel MPI, SGI's MPT, and Open MPI compared on Ivy Bridge, Sandy Bridge, and Westmere. So these are the different rates that you get on those different MPIs and on those different platforms. And so with the BIOS fix, then you get a very big difference in terms of message rate. So now Ivy Bridge Intel knows Ivy Bridge really well. So if you look at I've got a latency version of this one too, and OpenMPI knows things that Intel doesn't about latency on smaller messages. So I like to show this to the different MPI developers, and they say, okay, I'll go get ours to work a little bit faster. But the real importance here is that this has a huge impact on network design, right? So if because this was largely a draining issue, so the nodes had a problem pulling packets off the network. They didn't have a problem injecting them, and in a lot of our applications, you've got many nodes pushing down to a single node or to fewer nodes. So you're funneling down into nodes that can't actually take the number of packets that you would expect them to take because of some odd issue down in the BIOS. And so this, in fact, causes massive congestion and packet loss. We still have a problem with this. We don't completely understand what's going on, but we get transmit discards, and our transmit discards we're setting, I think it's 19 or something, the max, so it's a second, effectively. And so packets get stuck in switches for longer than a second, start being thrown away. And this can be driven in part by what's going on in the node. And so from a network design, can have big impacts there. And just understanding, okay, it's very difficult to determine that, oh, this was the node that was having the problem, right? Because it looked like the network's having the problem. And so, anyway, and then this is the bandwidth side of the story. So again, the fastest one here was the 10 threads on a single socket of the Ivy Bridge. with the Infiniband card plugged in the socket of that 10-core system, right? Again, Westmere's being the next 2 generations back. And so with the fix, again, everything gets better, but certainly coming up with this application to measure this, applications typically don't see this, so some of our benchmarks didn't find it because they're typically not driving the network that intensely for a long period of time. So you might see a slowdown within a particular part of the code, but the compute was 2.5 times faster, right, than Westmere, but network-wise it was actually slower, and so we still got a win because we're still computationally bound in most of our codes. So anyway, back to limitations. Well, congestion control. So I think congestion overall is getting worse for us because the nodes are getting much more powerful relative to where we were, and sort of the growth of network and the desire to increase the density of the machines. So the nodes more easily overwhelm the fabric, and so discards become more common. And discards can be caused by lots of things: errors in the fabric, cables retraining, nodes going down. All sorts of things can cause us to lose packets in the network, break reliable connections because the recovery mechanism for reliable queue pairs is too simple. And the 7 retry mechanism with the fixed replay is just not something that works at scale. So SM and SA requirements. So here's just sort of a list of things where subnet management is incredibly problematic still, I think, for very large systems. We have to handle the case where thousands of nodes are crashing or doing something really stupid. They're rebooting, they're being slow, they've got bad hardware in them. Especially when the system gets 10 times bigger, 100,000 nodes, and half of them might be doing something crazy. Well, I still want to use the other half, right? So there's also this issue of system maintenance and expansion. So when you're cabling up systems, a lot of times we're plugging in new switches and ports, and they got to go in the right place, or it's a problem. And so we want to do that live. We really want this concept around what GUIDs should be in the domain and what shouldn't, what ports are active and what are not. And so we've added some changes to the subnet management to do that. And that's quite useful. It could have 2 fabrics. So if you cross the fabrics, then that's really bad. And so anyway, large systems have lots of regularity in them. And so there's lots of static information that we can leverage off of. We really want static lid assignment. We have known ports that nodes will always be connected to. QP services for ARP and things like that. We don't want that QP number to move around. We want to actually be able, everything to be discovered locally, right? So the node should be able to discover most of the information it needs to know to connect to another node. And so we need to have the centralized service. It's going to get overwhelmed. It's not uncommon for us to see the subnet manager spit out, oh, I've got 180,000 things in my queue. I'm throwing the rest that come in away, right? And so decentralized or distributed services, static information, and really I think separating switch and HCA management is a fundamental change that needs to be made. That the routing piece between the switches is much more important than the node routing piece. And so that node routing piece should be static, right? That we know that the nodes are connected on all of these ports. And when I go out and discover what's out there route-wise between all the switches, I just want to program that and keep the lids for the HCAs in place and update the switch routing pieces as much as practical, right? So I mean, you have to have the the lid's pushed out into the route tables on the switches, but I still think there's a lot of things that can be done to make that more efficient. And I mean, some of this might be that you pre-computed degradations for the fabrics. You have your given to layout. Okay, if I can compute all the different combinations, if I drop a cable and I'll have those pre-computed and just push that out. Or maybe the switches know what they should be connected to. And so when the subnet manager scans, it just says, are you connected to who you think you should be at the rates you should be? Yes. And so are there any things that we can do to sort of reduce the load of what a full heavyweight scan is? And so that's practically at a large scale, it's just not going to work the way that it's designed today. So anyway, these are some of the things that we're working on. So overall, I think backwards, Infiniband's been key enabling technology for the strategy that we've used with Pleades and sort of carrying the system forward and through multiple generations of hardware in terms of processor technology, storage technology, network technology. All of those things have played really nicely. Certainly there's been certain problems that have been bad, but not something that's prevented us fundamentally from enabling users to do cool stuff with the models they're running. So future networks, I mean, interoperability between these networks. I mean, so Intel's working on something, and we've got, you know, Mellanox, and we've got RDMA, and all these things sort of in there in some place. And so when we sort of look forward, how we're going to tie these different things together, there can be a pretty big expense in terms of interoperability, and this is something we've leveraged off of, having this forward compatibility and backward compatibility between these multiple generations of Infiniband technology, which has been quite good. And so protocol translators, expensive hardware components, is bad, right? I think overall it complicates the systems. We have to have expertise, deep expertise in both of those technologies. And so going forward, I think the issue down at the bottom, though, is that the most important factor still is going to be what drives cost and performance of the compute, because that's our biggest investment. So that'll drive our decision process on how to move forward. And so this one is I don't know if I'm going to be able to play that or not. There we go. So that's a shuttle replacement launch. Modeling the trench, how they're going to change the trench, and I think that might be heavy lift. So there's two different launch vehicles that we're working on now for shuttle replacement. So there'll be one man-rated smaller unit and then a great big giant heavy lift. At least that's the plan. So anyway, that's all my talk. And any questions?
When's your next
well, we just completed last month, and so I think actually I don't know if we haven't integrated all of the last components. So I think there's about 16 or more racks that are coming in, or that are going to be integrated in a week or two. And but our cadence on this is typically 3 or 4 times a year. So it's a good chance we'll have something that comes in the summer. So because our budget cycle is, being September driven, right? So get towards summer, everybody says, okay, spend your money. So we'll go look and see how much we've got left and how much we had to pay out for various things. And so then we'll push out the rest and buy compute. And so right now we're incredibly limited by power. So we're pulling about 6 megawatts, and so that's our limit. And so we may have to deinstall equipment in order to install new equipment or move it into a different facility. Excuse me? Think about deploying what? Oh, virtualization. Yeah, so we're definitely interested in virtualization, and the issues really around virtualization are having to do with page registration and lid management. And so that's something that's getting worked on. And I think that's something that we would use as long as the performance cost was very low, right? So it's we'd use it for maintaining the system. So if I was going to say, okay, I wanted to say upgrade the firmware in this part of the system, okay, can I move all the work that's over there someplace else, route around it, so that none of my message traffic is going through that portion, then upgrade those switches and then reintegrate them. So the issue really for us is a lot of these jobs run for a week, right? So they're running a week, they're taking 500 nodes, the nodes are spread out all over the place just because they get fragmented over time. So virtualization would allow us potentially to move work or to garbage collect portions of the machine in order to enable maintenance, that sort of thing. As far as are there applications for virtualization beyond that, potentially for high priority work, right? So high priority work comes in, okay, I want to run this now. Right now I have to either delete work or they have to wait a little bit. But in terms of utilizing the hardware is fairly utilized, and virtualization doesn't give us a big win in terms of making better utilization of hardware. And in fact, most of the MPIs spin in their barriers, and avoiding that is hard. And then you have to have memory on the nodes, and most of the, a lot of the memory is used. So the typical use of virtualization within enterprise isn't really applicable to what we do. Okay.